Welcome back to Science Click. Today, we will try to understand the mathematics behind general relativity. To do this, we will gradually build all the mathematical tools essential to general relativity. To avoid overloading with content, this series will be split into 8 episodes, in which we will define each notion one by one, and that will be published in independent videos. The calculations and equations will be shown, hoping that everything remains understandable and intuitive. Each video will start with a theoretical explanation, followed by one or several concrete examples to see how the concepts apply. In this series, we will reconstruct each notion starting from scratch. It is therefore essential that we forget everything, all the notions that we think we know, to start from a blank slate. In front of us, a sheet of paper on which is traced a curve. This sheet of paper is an image to represent the structure of our universe, space-time. Space-time has 4 dimensions, but to simplify, only 2 of these dimensions will be represented. The curve that is drawn on the surface describes an object, for example an apple. This curve is what we call its world line. We will try to interpret this world line. To start off with, we slice the world line into small regular intervals. Choosing one point as the origin, we number these intervals one by one. In this way, we provide the curve with a graduation, which allows us to transform it into a series of consecutive points. These points can be interpreted as a trajectory. The curve is no longer an object, but a movement. It represents the movement of the apple through space-time. We have invented the concept of motion. These graduations along which the apple moves will be called the apple's proper time. The proper time of the apple is the time that governs its internal evolution. In a way, it is the time which would tick on its own clock. As it passes, the apple evolves and moves through the dimensions of space-time. From now on, proper time will be indicated by the Greek letter tau. Now that the apple moves, we want to describe its position as proper time goes by. To be able to locate a point mathematically, we will draw on our surface a coordinate system. Such a system is represented as a grid on the sheet of paper. This grid has an origin, a sort of 0 point, from which the grid lines are counted one by one. In this way, the position of the apple on the surface is described by 2 numbers, called its coordinates. It is important to understand that this grid is arbitrary. It has no physical meaning. It is simply a convention that we choose, an abstract tool whose purpose is to describe points using numbers. Depending on what situation we analyze, some coordinate systems will be more appropriate than others, and we will have the freedom to use whichever we prefer. Let us illustrate all these concepts with a concrete example. Imagine an apple falling vertically towards the earth, and that we observe from a great distance. As distant observers, let's consider what quantities we can measure. First, we can measure the distance between the apple and the center of the earth. As the apple falls vertically, this unique distance makes it possible to locate the position of the apple without ambiguity. In addition, we can measure time in relation to our clock, which will not necessarily flow at the same pace as the apple's proper time. In this way, we can define 2 coordinates, which we call t for time and r for altitude, which allow us to locate the apple in space-time relative to our perspective. As its proper time goes by, the apple will move freely and trace its trajectory within this coordinate system. We must be careful, however, to distinguish our time, t, which is a coordinate, and the apple's proper time tau, which represents the graduation along its world line. To understand, let's take an example. Say the apple passes through the point whose coordinates are 1 second and 7,000 kilometers. This means that when our clock indicates 1 second, we will measure a distance of 7,000 kilometers between the apple and the center of the planet. In space-time, it is crucial to understand that no object is stationary. Indeed, even if it does not move in space, like an apple which remains motionless on Earth, a body will always move through time, as the apple progresses every second towards the future. Objects all have a speed in space-time. The only thing that can change is how this speed is distributed between the coordinates of space and time.